I wanted to go over a few extensions of reactions that we just didn't have time to go over in a pandemic year. The first one reads, there are other types of single replacement reactions besides a metal replacing another metal. And I think you've actually seen a couple of these. So in this first case, you have aluminum, which is a metal, and then you have HBr. So that's actually an acid. So if you have a metal that reacts with an acid, it's going to potentially replace the hydrogen. Okay, now hydrogen technically is a non-metal, however, it can act as a metal because it can have a positive charge. So just like anything else, you would consult your activity. We're going to say this reaction happens. So when we're predicting our products, we're going to kick out hydrogen, okay, and then we're going to hook the aluminum up with the bromide ion. All right, but we got to do some thinking about this. Hydrogen is a diatomic element, so it's going to be H2. Also, that's going to be a gas. So anytime you react a metal with an acid and there is in fact a reaction, you're going to see bubbles because hydrogen gas is formed. And then your aluminum has a +3 charge when it's charged, and then your bromide ion is -1. So that's going to be AlBr3. Okay, this is usually going to be aqueous. And then you do have to balance it, which I'll just do in pink. So what would you need? A 2, 3, 6, and a 2. Okay, so now that's a balanced equation. Down here, we have a couple of reactions that are not a metal replacing a metal. In fact, if you look at the things that are most similar, it's going to be your halogens. All right, so knowing that fluorine is the more reactive, okay, you ask yourself, oh, is it already part of a compound? The answer is yes. So this is actually going to be a no reaction. Okay, we have what are called like opposite reactions here. So if one doesn't work, the other one has to work. So knowing that fluorine is the more reactive non-metal here, it can and will replace bromine in NaBr. Okay, so that means that bromine's going to get kicked out. So you're going to have Br, but bromine is also a diatomic, so it's going to be Br2. Now, interestingly, bromine's a liquid at room temperature. You don't need to know that. And then Na will get together, not F2, right? You can't just blindly copy those things, but Na plus, F minus, so NaF, and this is going to be AQ, and then you need to balance by putting a 2 here and a 2 here. Series. So on your activity series, there is a section that says reacts with acids, okay? And because aluminum falls within that section, go to your activity series. There is a tiny activity series for the halogens, okay? So the ones of interest are the F2 and the Br2. So fluorine is more reactive than bromine, meaning if it has a chance, fluorine is going to end up as part of a compound. This one's going to go pretty quickly. So you can write net ionic equations for a single replacement as well as double replacement, even though we've only talked about double replacement in class. So just like we know, anything that's ionic in AQ is going to split apart into ions. And then we dealt with precipitates, but now we have to extend that to gases and liquids. So if it's a solid or liquid or a gas, we're going to keep it together. So in this case, we're going to have Br2 gas. Okay, we're going to split apart the Na plus and the F minus and carry the coefficient down. Okay, yields, we're going to split apart because it's aqueous and ionic, the Na plus and the Br minus. And again, you're going to distribute the coefficient. And then we keep together our gaseous F2. So now we're just going to cross out the things that occur exactly the same on both sides. And in this case, it's only one spectator ion, which is the Na plus. What you're left with is the net ionic equation, which I have written here. Now, something for the next extension topic that you'll want to take a look at is the fact that you have charges on one side. So this is 0. This ends up being a -2. They have to equal the charges on the product side. So not only do you have to balance equations in terms of number of atoms, you also have to balance them in terms of charges. So we have a 2 negative here and a 0 here. So 2 negative and 2 negative matches, we're all good. Our third extension topic is writing half reactions for single replacement reactions. So single replacement reactions, and some other types, but we're going to focus on single replacement, are what we call oxidation reduction reactions. Now there's another term you can use called redox. Okay, it means the same thing, reduction, oxidation. But I want you to focus on the definitions of oxidation and reduction. So oxidation is the loss of electrons, and reduction is the gain of electrons. And these things always happen together, right? You can't lose electrons and something else doesn't gain them. So oxidation reduction will always occur together. And we were talking at the very beginning of the unit, we were identifying types of reactions in the first POGL that we did. Hey, did anything change charge? Okay, we use the terminology change charge. And if the answer was yes, that means you had encountered, without knowing the term, an oxidation reduction reaction. So anytime you have a redox reaction, you can write something called half reactions. And that's just looking at the part that is oxidation separate from the part that is reduction. So in this example, I'm going to assign everything a charge. So remember, elements have no charge. In their elemental form, it's just a charge of 0. So zinc has no charge. Here we have an ionic compound. Okay, we know that nitrate is -1. That's as detailed as you have to get with that. If we have 2 of them, that means that the charge on this lead ion is +2. If you go over to the product side, lead is in its elemental form 0 charge. Okay, nitrate doesn't change. So nitrate is actually a spectator ion in this case. But the zinc does change to a +2. So there's been an exchange of electrons here. That's what we mean by oxidation reduction. If we suss it out to say, okay, oxidation, this is the loss of electrons, it's actually your zinc here that lost electrons. So it went from having a 0 charge to a +2. And how do you get to a +2? You lose negative charge. So our oxidation reaction is going to be zinc going to zinc 2+. But what I just told you on the previous slide was that you can't have a 0 charge on one side of a reaction and then a different value on the other. So what you're allowed to do is add electrons. You can't subtract electrons, you can't do anything with protons, but you can add electrons. So if we add 2 electrons to the product side here, and then we say, okay, here we have a total of a 0 charge, here we have a +2 and a -2, that's a total of a 0 charge. Now our charges match on both the reactant and the product side. Also, oxidation is losing electrons. Oh, look, our electrons are on the product side because they've been lost. Okay, now who's going to gain them? Well, whatever gains them, that's going to be the reduction half reaction. Okay, so if we look up here, it looks like our lead went from a +2 to a 0. So it was reduced. So lead with a 2+ charge, so just get rid of the nitrate. We're only honing in on where the electrons actually are being exchanged, to lead with no charge. Again, we have to make sure we have the same charge on both sides. So we're going to add 2 electrons here. And that's our reduction half reaction. Reduction means electrons are gained. Right? Now, one other thing, which was super easy here because we had coefficients of 1 in all cases. Your number of electrons lost has to match the number of electrons that are gained. So what I want you to do is predict the products and then write the half reactions for this reaction. Pause the video, and then when you're done, you can replay it and check. So now you can check your answers. Probably the trickiest part here after assigning the different charges, right? Even though there are 3 bromide ions, it's still a -1 per bromide, and that's what you care about here. I think the hardest part is with this oxidation reaction. Sodium is losing an electron each of 3 times. Ooh, and I just caught my mistake. But you pull down the coefficients. So this will be 3Na, pull down this coefficient, this will be 3Na+. Again, we're ignoring our bromide ion because it's a spectator ion. So here you have to add 3 electrons because you need the charges to match on both sides. So we have a 0 charge here, we have a +3 and a -3, going to give us a 0 charge here as well. Also, the number of electrons we're losing, which is 3, is the same as the number we're gaining, which is 3, and that has to be the case. Last extension topic. What if you have a decomposition reaction that is not binary? So remember what binary means? It means having only 2 elements. So take a look at these 3 options. Which one is binary? Okay, it's that guy. So that's easy. It's just going to split apart into its elements, which are calcium and oxygen. You have to remember your diatomics, and then you do have to balance the equation. Okay? These other guys, though, are a little bit different. So LiOH does not just split apart into lithium, oxygen, and hydrogen. Instead, you kind of have to memorize it. So metal hydroxide split apart into the metal oxide plus water. Okay, how do I know that? Because I memorized it. How did scientists know that? They noticed a pattern. Anytime they had a metallic hydroxide, it was always breaking apart into the same thing. The only difference was what metal was there. Okay, of course, you'd have to balance this. You just need to put a 2 out here. And then lastly, we'll do the calcium carbonate. So metallic carbonate split apart into the metal oxide and carbon dioxide. Okay, and that one's already balanced. Do you need to memorize these at this point? No, but in future chem classes, you may have to, and I just didn't want you to be unaware.